So we'll continue with our Astronomy 1 lecture, Chapter 4, which is about the Earth, the Moon, sky, and today we'll look into first two sections, Earth and Sky, and the seasons. Mostly we will learn how to locate things, to find specific locations on Earth, a scientific method to say, okay, where I am exactly located. In these days, we have given names to place, and you can say, okay, let's meet in front of library, or where is that tree that, or you can say in front of library, behind the Mac, or UC. But if you are somewhere far out, middle of nowhere, then it's hard to give reference point. For that, we need to find a universal reference to find locations. Those are coordinate systems. You can say, okay, let's meet in front of the library tomorrow, but that's not enough. We need one more coordinate system. Yes, the in front of the library is a coordinate system, but you say you meet tomorrow, but what time tomorrow? So time is also a coordinate system. But today we'll only discuss the two coordinate systems that can define a point in space on Earth. And we will extrapolate that information, and we'll also see how we can pinpoint a location in the sky, our celestial sphere that we defined in Chapter 1. And we'll also look into how or what causes seasons on Earth. Why do we have temperature variation going from December towards June, and then we're talking about mean variation. Day to day in Texas, you can have 80 degrees today and you can have snow next day, but that's not the point. We're talking about average temperature increase per week or per month. Temperature starting December 21st, it starts to rise and gets peak around June, and then it falls again. So why is that variation? We will look a geometrical answer to that. And so on Earth, we to find a specific location, we define two things. One is the latitude and one is the longitude. These two coordinates. And as you can see in the diagram, this is the equator, Earth's equator, and we consider Earth's equator to be at 0-degree latitude. And as you go up, it's from equator. You can go every degree rise in the arc because it's a circle or it's a sphere. We can go every degree up towards the North Pole and make that 90-degree pathway. So this is my elbow. Consider your elbow at the center of the Earth. Now this is the equator, right? So that's 0 degrees, and raise it every angle, and when it's vertical, that's 90-degree rise going from equator to the North Pole, or the other way around, 0 to 90, or you can call negative 90 because it's downward direction. So that's the latitude. So that's one dimension. But to find a point of intersection, we must have two dimensions, two axes meet at a point, because one axis can be long, right? So this table is always long. If I want to point where to meet or where to sit in this table, I need another line which can intersect, and that intersection point is the location I'm looking for. So we define another lines, the longitudes, the lines that run from North Pole to the South Pole. Those are called line of longitudes. And similarly, we use similar idea to map the sky. We'll see that next. Here, the great circle, some definition. Great circle is the largest circle that forms in a sphere. Like the equator is the great circle here. It's also it also has the largest radius from the center of the Earth. That's the great circle equator here. And for example, the city defined here, whose location is defined, Washington DC somewhere here. If we were to say where is Washington DC located, if you go some degree north of the latitude, this is my latitude, some degree north, that's 38 degrees, and 77 degrees west in the longitude. Okay, so this is my longitude from that point, and that longitude is called the Prime Meridian. Okay, for latitude, it was easy to set that point because it's the largest circle and it's the equator of the Earth, and say, okay, every degree up or down, let's measure that as the latitude. But for longitude, it was not easy. It took forever for everyone to come up to a conclusion. In 1984, finally, all the countries agreed, and back then, England was top in terms of it was an empire itself for a long time, and they had the most power, I guess. And so they said, okay, the city called Greenwich. Do I mention that here somewhere? Greenwich, England. Okay, they said, let's draw a line that goes through Greenwich to North Pole and South Pole, and call that the Prime Meridian, or the starting point. Because Earth is a sphere and it's a circle, there is no end point, right? So somewhere we had to break the symmetry and call that as a 0 degrees, and we said, okay, Greenwich, that point is the longitude equals to 0 point, and let's go degree to the right or degree to the left to define that coordinate system of longitude, or call that prime meridian. And from there, when we say Washington DC is 77 degrees west, meaning 77 degrees measured from the Greenwich prime meridian line. Okay. And so it goes from 0 to 90 up, or minus 90 down. That's the latitude, and longitude you can go, its total is 360, you can go around this way towards the left, or you can go around the other way with negative 180 or positive 180. That's the longitude. And that's how we measure a specific location. That's, when you say, okay, we have a GPS location, usually, it measures these latitude and longitude points. Now you can measure any point on Earth, we can measure in terms of latitude and longitude where that point is. And our reference, we need a reference line always to measure, right? And that's equator for the latitude and the prime meridian for the longitude. It's the actual image of the prime meridian in Greenwich, England. And also they have a Royal Observatory there, which contributed in a lot of astronomical observations back then. So it did have some astronomical perspective or historical reason to set Greenwich as the prime longitude and location, or where the longitude begins. And so we can extract or we can extrapolate this information that we have on Earth, how we define a location going up and down in latitude and longitude, the sideways or around the Earth as longitude, and so we can just expand this outward into our cosmic or our celestial sphere. Right? And so we can extend our North Pole up to our celestial pole, celestial North Pole, celestial South Pole, up and down. Here is our Earth. And so every rise up, the equivalent to latitude, we call this the declination. To go up, that's the declination. Go from, again, 0 degrees, so equator is projected outward. This is our celestial equator now. Earth's equator is down here, and so the celestial equator is projected out, and from there, that's the 0 degree declination, and goes up to 90 degrees and minus 90 degrees towards the south celestial pole. However, for the longitude equivalent is the right ascension, and it was not much of a conflict there to set the starting line, a 0 degree line for the right ascension, because the plane of the Earth and the equatorial plane and the ecliptic plane of the ecliptic, because our rotation axis is tilted at 23.5 degrees. Now we know the ecliptic is inclined at 23.5 degrees with the Earth's rotation plane, and so these two planes intersect at 2 points. And this point is called the vernal equinox, and we said, okay, let's set that vernal equinox at 0 degree RA, right ascension, and go around 360 degrees this way or that way, and and that's called the right ascension, and this intersection point is called the vernal equinox. So we have declination, right ascension, vernal equinox. We're already used to with the celestial equator and the plane of ecliptic or ecliptic, the path of the sun. It subtends in the sky. So the right ascension can be measured in terms of degrees or hours, because it takes 24 hours for the Earth to rotate. It completes 360 degrees in one complete rotation. So that 360 degrees divided by 24 hours is 15 degrees arc. So every hour, so we can measure the right ascension in terms of degrees. So 15 degrees to the right or to the left, let's say, these lines here, if these are 15 degrees apart, going from this line to this line, so that means they have subtended an arc, or it took 1 hour rotation time for the Earth, or Earth rotates, let's say, for 1 hour, and I'm looking at certain direction towards the right ascension here, and in 1 hour I'll face some other direction. That change is 15 degrees. We can measure in terms of hours or degrees, either way. And so that's how we locate most of the stars in the sky, at what ascension, right ascension, and what declination. Next is, let's look at seasons now. We have, in general, discussed before. Let's try to be a little more specific. What causes seasons? What do not causes seasons in our solar system is the orbit of the planet around the sun, or the shape of the orbit, which is the eccentricity of the orbit. We know that every path of the planets around the stars are ellipse. However, our planet's eccentricity is towards zero, hence it is very, very circular, not exactly circular, close to circular. So that does not affect the temperature on the Earth, the eccentricity. They're like our Earth is like this, very circular orbit around the star. So let's forget this or circular orbit. There are other planetary systems with very high eccentricity, and like, for example, this one here. In such planetary systems, the eccentricity or the shape of the orbit would affect the temperature on that planet. Whenever that planet is at the periastron, you can see it's very hot. It's very close to the star. The temperature is too high around here, and as it goes farther away from the star, it gets cooled down. Right? So it can be very icy, frozen state at the apastron, and liquid, even vaporous state towards closer to the sun. But it's not the case for the Earth. But then what causes the seasons? What causes the temperature variation is the tilt. That 23.5 degree tilt, Earth's rotation axis with the plane. And so how does that affect? Well, that, during its path around the sun in a year's time, at some point here, at that point, the rotation axis is directed away from the sun, and northern hemisphere here is inclined or leaning away from the sun, and when it moves around between these 2 points, these are called Vernal Equinox and Autumnal Equinox. Autumn in September and Vernal Equinox around March or March 21. That tilt does not affect much how much solar radiation is received on the Earth, and the days are mild, the nights are mild. We get equal amount of temperature in the northern hemisphere and the southern hemisphere. But when it comes around June 21, as you see now, the leaning of these northern hemisphere is towards the sun, and it receives more sunlight, and it's hotter during the June-July time, and again in September it's equal amount of radiation received in north and south hemispheres, and so we have springtime and call this fall time, autumn. We don't use the word autumn that much around Texas. We just call it fall and spring. And so that's one of the reasons, 23.5 degrees tilt. But what's the physics behind it? What's actually happening? There are 2 reasons that the temperature rises, and one of them has to do with the surface area coverage by the light, because that because of this tilt here, okay, which is equivalent to that, this angle is bigger. So here, sorry, the sun rays that strike the Earth with respect to the surface is bigger. And so let's assume that we are getting light in 1 meter square area only, and it's directly from the top. The intensity is high. And the same 1 meter square beam of the sun in the winter, because it's leaning away, same 1 meter square area, that beam is now spread over twice the surface area of the Earth. So same amount of heat is distributed in a larger area, so the temperature drops down. That's one reason. What's the other reason? Reason 2 is the time sun spends over our sky during the summer months, and you have noticed it, summer days are longer. Right? In Texas, it can be as long as 15, 16 hours of daylight. Again, because of that geometry, because of that tilt, during the summertime, sun rises, far north, towards the north, and travels longer path in the sky, spends more time, so that it's direct, because the angle is bigger, more intense sunlight, and we are receiving that high intensity sunlight for longer amount of time compared to winter and summer. That's about 9 hours versus 15 hours. 9 hours around winter time, and we get 15 hours. So we're getting more insolation, more radiation from the sun, and so summers are hot. So again, these two reasons are very important to understand seasons on Earth. And some more definition here. Sun's illumination on Earth. By the way, any question before this one here? Please don't hesitate to stop me. We can discuss it. Or maybe I move forward. I want, please, you can notice this if you haven't noticed. In winter time, the sun, if the left wall at the east and west, sun rises from towards the south, and it spends very less time. It goes like this in the sky, and it spends less time in the sky and sets in the west. As days progresses, going from December 21 to June 21, then the position where the sun rises shift towards east and north of east eventually, and it follows that larger circle, and you will see different time. Because let's say usually undergraduate students are not morning person, I know. I've been there, and so you can check out the sunset times. In the winter you will see sun setting far to the left, that's our west, south of the west. And in the summertime, the position shifts like all the way to the right towards north of east. And you'll see that position difference. And so two more definitions here, the Capricorn, Tropic of Capricorn and Tropic of Cancer during the summertime here, summer in the northern hemisphere, at some latitude because of that 23.5 degrees, so 23.5 degrees above the equator. So this is our equator here. And 23 degrees above the equator, and on that point, the sun is on the zenith, directly top of our head. If you are standing at that point, that's about where Hawaii is. And that line here is called the Tropic of Cancer. And on the top, there is Arctic Circle. On the bottom, you can call that the Antarctic Circle, and that's the Equatorial Circle. And so here, as you go above the equator, the daylight time increases. And right on the axis of rotation at the North Pole, it's all day. The sun never sets for at least 3 months, June, July, August, or so. Its sun appears to set, but it grazes through the horizon and it goes back up again for about 3 months. And the effect is felt in the Antarctic Circle, where they have whole 3 months of winter, no sun. And again, that's just a shift. Now during the winter, everything is reversed between the North Pole and the Northern Hemisphere and the Southern Hemisphere. Same thing, that point here, 23 degrees below the equator, where the sun is directly above the zenith point. Along the zenith here, that point, that line is defined as the Tropic of Capricorn. And so to summarize, set this image, when you close your eyes, you should be able to imagine this diagram. This schematic here, the equatorial plane and the ecliptic plane crossing each other at 23.5 degrees. This is the path of the sun if we give one other thing. Again, it's relative. We're saying this is the plane, this horizontal plane is the plane of the sun, right? That's the ecliptic. Then Earth's rotation axis, so this is the plane. Earth's rotation axis, that's at 23 degrees, like this. But if I want to match that rotation axis, make that vertical, then I can rotate everything by 23.5 degrees, and now the sun's that ecliptic plane seems to be inclined. It doesn't affect the whole geometry part, because we are rotating the whole axis by 23.5 degrees, and that's what we see here. That's the that's the ecliptic plane, and that's the equatorial plane here. This is the ecliptic plane. The sun moves, in that direction here, and these 2 points or these 2 planes virtually intersect each other. I mean, not in real life; these are just imaginary lines, right? Virtually, they intersect each other. That angle is 23.5 degrees, and these 2 intersection points are called again Autumnal Equinox, Vernal Equinox, and when the sun is at that point here, southernmost point, that's called the winter solstice. That's the summer solstice. Vernal equinox, we are almost there. 18, 17 more days, and we will get. So we started here summer. We're going, so we're almost there around here with respect to sun. And so whenever it's at that point, when the sun is at that point, then sorry, the vernal. We are here. We'll get to. I lost the track. I thought we're going from summer to fall. We're going from winter to summer. Time goes so fast, sometimes you forget to keep track. And so again, we're going this way. So when sun reaches at that point, that intersection, vernal equinox, in 17 days, you may have realized that daylight time is increasing. Okay. When you hit that equinox means equal time, equal day and equal night. The actual daylight time or the dark time, 12 hours each. And after that, we move towards the summer solstice, and the daylight time starts to increase, and during the summer solstice on June 21, we have the longest day, and then sun starts to move around that direction. Actually, we move, but it's relative again. And the days are shorter, and the shortest day, no, that's the equal day, equal night, shortest day, and that thing, rotates every year. There's one more thing I'm sure you haven't forgotten, the precession of the Earth causes, that the rotation of the axis, Earth's axis, is not always pointing in one direction. That thing precesses like this, and it takes 26,000 years to go around. So for our lifetime, 70, 80, lucky if we live 100 years, very rare case. And in our lifetime, that precession change is negligible, so we can expect the seasons to be continued this way in our lifetime. But in the celestial time clock, yes, that will be different. Different because the whole thing that's pointing this way now, if it points the other way, the summer solstice will be actually the winter solstice. So in June, northern hemisphere will pass through winter, and in December will pass through the summer days. It will take half the rotation of that precession line, precession axis. That's about 12,000, 13,000 years. Okay, I'll stop here and we'll continue Earth, sky, and moon on Tuesday. Thank you, guys.
Thank you.